Matt and I have known each other largely in the context of microsystems, or MEMS maybe. You've heard the word MEMS. Who knows MEMS? Oh, good. Well, you will know it after you leave today. Okay. So I had a chance to talk to Matt, Adrian, Curtis, right? It sounds like there's a considerable variation in your background. What I'd like to do, hopefully to help you folks sort out engineering and the discipline at large, is perhaps take you through two discussions today. One primarily has to do with what perhaps can an engineer do to create a skill set. And perhaps this is broadly applicable to whether you want to be a chemical engineer, petroleum engineer, design engineer, software engineer. God forbid. We got to have software though, right? You know, it's great stuff, right? And then secondly, talk more about this field of MEMS, right? And perhaps show you what happens when you start to cross disciplines in engineering. Some very exciting things, and I think you'll see it in your products today, right? What's happening, you know? Amazing things, right? I mean, this thing is amazing. Anybody taken one of these apart? Who owns a smartphone? Jeez, everybody's got one. Has anybody taken it apart? You get an old one, right? I mean, what are you going to do with it, right? So you take it apart, right? It's got a big, huge battery in there. Right? Tons of electronics that you can hardly see anymore. Right? Tons of mechanics. Right? A nightmare in packaging, and materials galore. Right? Probably every material base is present in this thing. Right? And I'm going to talk about a component which has been tremendously helped by this product, by mobile electronics, and hopefully give you some context about how, you know, you see yourself in your engineer career, and maybe you don't think this is a formal area of study, but I would encourage you not to hesitate if you have passion about something. And at the end of the day, right, maybe blaze your own trail, as it were. Good stuff, right? So I've been an engineer all my life. I had an opportunity to work originally at a telecommunications company called E.F. Johnson in the 80s. They made cell phones in the 80s. Has anybody seen a cell phone from the 80s? Right?
Is that the one that comes with the suitcase?
Yeah, well, that's optional, but it's the upgrade version, right? Okay, and you better have two arms, because that thing, you know, weighs a ton. And if you did this to it, the display would make funny, crazy alphanumeric things, right? Incomprehensible. And my first job was to measure the field strength of a cell phone in southern Minnesota in the summer. I don't know if anybody you're familiar with southern Minnesota, but one thing that happens over the course of the summer is corn grows this way, right? That makes a tremendous RF barrier. And so the summary of that was RF signal does that from June to August, okay? That was what I learned. And I did it on an Apple II. Great stuff. Anyway, it was kind of a foretelling thing, because probably the computational power was about 1/millionth of this thing at the time. All right, it really made some great strides. So primarily what I got involved in is what you might call design engineering, right? That really turned me on, right? Designing microwave circuits and things, electronics. You know, of this section, who's interested in electronics more, in electrical? Okay, who's more mechanically interested, maybe? Thank you. Any chemical? Okay, materials, I heard some people interested. Okay, how about software? Software more? Coding? Hard code or? Okay. Petroleum engineering, this sort of thing? Right? Yeah, okay. New Mexico's got a pretty good interest there, right? Hopefully all this I'm going to discuss pertains to largely those areas, right? What I've noticed, right, is that when you start to gather information about your specific trade, you kind of accumulate this, it's like a toolbox, right? And this toolbox contains multiple tiers, right? With the top tier, kind of the things you pull out a lot, okay? You got your Phillips and you got your, regular straight blade, right? Okay, right on top there. And this toolbox grows. It grows. How does it grow? It grows because you read trade journals. You say, oh, this cool material is now available, right? Didn't know that. Didn't know you could buy carbon nanotube stuff and put it in a 3D printer. Can you do that yet? No.
I don't know.
Okay, I don't think so. Anyway, you find out stuff by reading, right? You used to go to the library. You don't have to much anymore. You can go online and find all kinds of things. Engineers have to stay abreast of what's emerging technologically, right? Have to stay reading. Right? You can't leave school and just sit on it, right? You keep adding things to this toolbox, right? You say, oh, maybe this piece of electronics is better, right? You look into it. You have to keep building a toolbox, right? Part of this toolbox comes from school, right? F equal MA. Yeah, right. Got to know that, okay? Got to know circuit laws. You're doubly, that sort of thing. And so you add to this thing. You keep on developing your toolbox. And what I find is there's about 50 to 100 things you just keep on coming back for. And those become your core, right, that you use. So I encourage you to think about building your own toolbox, right? It says a lot about what you're interested in. And perhaps it can reveal the type of study that is lacking, right, that you need to know about, right, or that you enjoy, quite simply. So that's kind of an underlying thing. You've got some skills that come in here, okay, of various kinds. You've got information. Okay. Then there's a certain discipline that goes along with this. Okay, and some people call it an attitude to engineering. There's a issue of responsibility, right? Designing things that are safe, that hopefully don't need warranties. Okay, that comes into this. Call this an attitude. This is critical, right? Whether you're working in a big firm or a large firm or by yourself or consulting, right? I'll mention some things about that. And then over time, you may have different jobs and you reflect on those and those form your experience set, right? Okay, measured signal strength of a cell phone. What do you got to do? Well, you got to have a computer. You got to take a lot of data. So you got to know something about writing a little bit of code, interfaces, whatever. You got to know what dB means, right? Decibel. Okay, you got to know a bunch of terminology. Okay, all this kind of stuff, right? And you go to your next job and you start building what? Experience, right? The tough word, right? How are they going to hire me without any experience? Okay, never done anything. Well, I'll let you think about that for a second. in any event, most of what I do centers around design engineering, and that feeds off of a problem. Okay? So I work in a components industry. A lot of customers typically want something that isn't available, maybe completely. It's not even an improvement to something, just never existed. All right? But the first problem I find is defining the problem. Right? I bet Matt hasn't talked about that yet, right? What is the problem? And it's quite amazing, but it's one of the most challenging aspects of engineering. Customers never tell the truth, right? They lie like crazy. They'll either say something they don't need or completely misinterpret what's needed. It's not their fault, because they're always right? Yeah. That's just life. But it's a challenge for an engineer a lot of times to kind of bring out that real problem. What's the essence of the problem? Right? Did this maybe have was it an issue of a vendor that they had? All right? Was it really a fabricated device to begin with? Right? Or is the design just doomed to failure? Okay? Or is it something that's completely unrealistic that they want? You have to get to the root of the problem. And you have to agree to it. Right? What comes out of it? Some kind of specification. Right? What's a specification? Right? What things are in a specification? Right? Numbers. You got data, right? Right? Numbers like it's got to operate from minus 55 to 125 C. Right? And until you write those things down, they're sort of up in the air. So, technical writing is I heard there's a technical writing course, huh? At some point. Yeah. Extremely valuable. If you have the time and it fits in, take technical writing. If you take any English course, take technical writing. Right? It's wonderful stuff. It'll help you to create documents that are easy to read by other people, whether they're engineers or accountants, okay? Or marketing people. They're all important, right? But you got to write a spec. It comes from defining the problem. A good spec is created if you define the problem appropriately, right? So you discuss the customer, okay, what the problem is. You want to create some concepts, all right? Some ideas about how you solve the problem. Clearly, there's a lot of input to this, right? Some people mathematically inclined might call them boundary conditions, right? i.e., it can't cost more than $1. Might be one boundary condition. That sort of guides my concept, or maybe it helps me to already choose the concepts that I'm interested in, right? Okay. Where could that come from? It could come from the customer, right? It could come from the marketing department, right? Right, and there's some cross-interaction there, right? It could come from peers. Maybe you say, hey, we got called up this customer, and they say they need X, Y, Z, and you talk to your buddy John, and you say, yeah, I heard that before too, right? Okay, maybe there's reaffirmation of that. Basically, there's others, right, that can help to guide the concept. I hear some people here are maybe acquainted with IC fabrication, chip fabrication, do chips, great. So a lot of times this might be guided by a process or a technology that's available, all right? And if you're at company, say Intel, and they're running process XYZ. Well, it's got to be able to be made with that process, right? Or that material. You find yourself on a long and expensive path to develop your product. But what I really want to impress upon you is that at this point, you really haven't done any analysis. You're not doing any calculations per se, other than the ones you might be able to mentally do on the fly, right? And what I might also emphasize is that I don't know if this is a category of things that somehow gets addressed in engineering, but
yeah, I think there's some engineering classes where they talk about the economy of doing engineering and economics of economics and estimation is part of that.
Yeah. Estimation is a thing you want to develop tools around in your toolbox. Whether it's to estimate whether that product that the customer is describing is realistic, or whether you think you can make the product for a given cost, whether you can do it in a timeline, that's pertinent, right? So we talk about schedule, cost, right? These kind of things.
Project management.
Yep. Critical, right? To bring along. Every engineer has to do this, right? And what does it look like? You ever started with a product and you say, can I do this or can I do this? A lot of times what a customer will ask for is, give me a ROM. Anybody know what that means? ROM. An estimate. It is an estimate. What does that stand for? Rough order of magnitude. Rough order of magnitude. Is it $1 or $10? Okay, is it going to take a year or 10 years? Order of magnitude. Factors of 10. Okay, some people do this, right? Very rough order of magnitude, right? Can it happen in your lifetime? Or is this something that's going to be in the 23rd century or something? Okay, well, we don't like to do that. You do a ROM, okay? Say, okay, yeah, that's maybe reasonable. We can do that in 6 months, and we think at volume we can hit the under $1 cost, right? Then there's more detail, as you proceed down this path of engaging a customer, right? They'll say, okay, yeah, you're reasonable now. Show me a schedule and cost, right? And there's all kinds of things, PERT and blah, blah, blah. They'll give you all these other acronyms that you can use as guides to help determine what the product development looks like, okay? That's what engineers do every day. Estimate. Give me a ROM for that, okay? Anyway, so you've got a concept. Now you've got to turn this into some kind of a testable device, okay? How do you test a mechanical design? Okay, I'm making a door latch. All right, you think they just took the door latch design and started making 10 million of them right away? They just churn them out. Probably didn't do that because it took the door latch design 16 before they liked it, right? Okay, so you got to be able to test things, right? So there's this notional idea of testability. Kind of got to have in the background of your mind, right? Geez, if I make this, I really got to test it, make sure it's working, okay? Design for test, this is called, right? It's also something called design for manufacturing. Can I make it? Okay? Manufacturability. Sorry about the words. Manufacture, can I really make it? So these things sit in the background, right? They're in your mind, right? Can I really pull this off? Okay? And I kind of want to notionally be satisfied at this stage that yeah, okay, these concepts are not totally crazy, all right? You've heard of brainstorming probably, right? What's brainstorming? You just get in a room, you say anything, okay? I'm biased, so don't take this to heart too much, but brainstorming's never worked for me. It's tough. You know, it maybe helps jog your mind loose so you kind of think about things. But ultimately, there's significant constraints on engineering, right? Particularly today on cost, right? Labor, materials can be very expensive, right? If you're not careful, right? It puts you out of the picture. So you come up with some concepts, okay? I mentioned this toolbox, right? Well, let's bring in the toolbox, okay, and start to use it, okay? I mentioned all the things that help to populate this thing. But this toolbox is going to come in here and ultimately help you make a design, okay? And we'll call this a prototype design, as it typically is. Initially, right? What's a prototype? Right? Kind of the first thing you make. Rough draft. Some people call it brass board. It can develop into a more mature thing ultimately, but it's definitely not going to go to production tomorrow, right? Okay, has to be tested. So you come up with a design. And what do you have to do? You have to do some calculations to do that, right? Right? In my toolbox, I've got some things that let me do analysis. Okay? They could simply be this. That's a good one if you're an ME, right? But there could, in other words, there can be equations, and you write stuff down and you start calculating, right? What's popular today is you may do some computer-assisted design, all right? Some numerical design, lots of software to get bogged down in, right? I don't know if they still use Spice today, do they? Spice. I used to call it Lost in Spice. But you've got tools to help validate your design. On paper or on a computer, virtually, okay? Virtually, right? You get this design, you work on it, you talk to the customer, you say, market likes it, okay? My friends say, yeah, you're not crazy, okay, I can test it, I think I can make it, I've done all the numbers, looks pretty good. What do I do now? Something called a design review, right? It's kind of like the final exam, okay? And you ask the question, or the group, right? This is always a team. Did this meet the spec? Don't forget about the spec. Right? This is what we're trying to do. Is this going to really meet the spec? If it's not, hey, go back. Maybe you have to go back here. You know, maybe you have to go do some more number crunching. Right? But you can't go to the next step, which is make it. That was called fabricate it. Right? You can't go to that step unless it's past design review. Okay, you make it. You make the first article. Some people in the defense industry call this a first article. A first article gets kicked, dropped, temperature cycled, beat up, cussed at, everything you can think of, right? Tested to see if it met the spec, right? And this occurs in software, right? Get the bugs out. Okay, it occurs in mechanical engineering, electrical engineering, if you're making anything. So you folks are really at a great spot, right? Some of you have experience, you can reflect on this. You are at the stage where you can fill your toolbox with whatever you want, right? Whatever you're interested in, right? And fortunately, Professor Plyle has come with a course that helps you reflect on this now, not after you spent 4 years going through 50 engineering courses, right? That you didn't want, which can happen all too often. So that's important. That's important, I think, as far as I can tell, for any engineering discipline. Knowing this sort of core tool set. If you're doing optics, right? You have any interest in photonics and LEDs, maybe, something like that, right? You build an optical toolkit, right? Optical engineering, what do? Right? You're looking for photons instead of electrons or mechanical strain, okay, right? That good stuff. So, there's one other thing I mentioned. Anybody have questions about anything come up? By all means, please ask them if you do, right? How do you decide what design to choose and go forward with, right? Maybe you have several designs. Maybe you have competing teams. You know what they do at Google today? They'll have a problem, and they'll define it. And they'll have 2 teams in the room. And that's the only time they ever see each other for the next year, right? One team goes that way, one team goes that way. And they come back, maybe not a year, maybe a month. Can't afford that. And they pursue completely different things. And it yields completely different results, right? Maybe. Yeah?
When would you do the cost and quality analysis?
Quality, I'm glad you mentioned, right? So many times people will say cost is the first design parameter. And I think it is in most cases. So immediately, if you get a problem and you can't do it for under $1,000 and it's got to go into a mobile phone, that's a problem, right? So cost has to be appreciated right off the bat, right? Quality is about getting feedback. You can call it quality of design, quality of the design process, but basically it's a measure to give you feedback on how far off you are from your desired end, right? Which in this case is a workable design that meets all the criteria in your specs. You can measure that, okay? More commonly, people think of it mapped into manufacturing, right? And then you get to do a lot of statistics, as Matt tells me, it is taught in the school, right? So quality is through the entire thing, right? Always thinking about how to improve. Continuous improvement, very important concept, right? Something failed. What do? Just forget about it? Probably not a good idea. You can always learn, right? Those are tremendous opportunities. So quality permeates every aspect of the design cycle, right? And production. Very important, right? But cost is number one, really. If you're talking to your customer and they don't identify cost, and they'll play a game, right? They'll say, how much is it going to cost? And you say, well, how much do you need it to cost? Well, show me your numbers. Well, show me your numbers. Okay? It's a tough world, right? You gotta wiggle your way through that, right? And try to find the answer. Try to find, really what they need. A lot of times you have to interpret between the lines because they will not tell you outright. There's a bit of an art to getting the cost well defined and well understood. I don't know if that answers your question entirely there, Matt, but it's really important to consider cost initially, right off the bat. Okay, so we talked about different engineering disciplines and how it might be applicable. I think what I just wanted to point out is something that seems to be accelerating in time. It's existed for a while, but today it seems it's even more prevalent, right? And that's this idea of interdisciplinary engineering. What do you mean? Like bioengineering. Seems like an oxymoron. Right? Or, I dare say, psychoacoustics. Right? Like acoustical engineering of what does that mean to the brain? Right? These are things. But today, I think you find tremendous advances occurring because of these cross-interdisciplinary interests. And I'm going to mention one big one and talk for the rest of the time about it. And that's this term nobody knew. Okay. Which is MEMS. MEMS. It's probably not in the Webster's yet, but it's pretty close, I would imagine, by today. Okay? MEMS resulted from cross-interdisciplinary between what? Between mechanical, okay? Right? Oops, sorry. Mechanical. Between electrical systems. There is systems engineering, right? Okay. Having an overview, a broad idea about maybe I'm making a ultrasound, right? Right? Go and you look at bones, babies and things, right? Wow, I've got sound, right? Got electronics, mechanics, software, okay? And someone's got to integrate all these things. So I guarantee any ultrasound company is going to have a systems engineer figuring out how all this stuff connects together in interfaces. But MEMS really is associated with things that are on the micro level, right? Miniature electromechanical devices. Micro electromechanical systems is what MEMS stands for, right? Right. Tremendous amount of overlap between all material science, electrical engineering, chemical engineering exists in this field, right? What does it make, right? It makes the thing that says, hey, you're open, okay? It makes the thing that said, hey, you sit down. It makes the thing that tells you where you are relative to where you were this morning, right? Gyros, accelerometers, right? All those good things. That's what MEMS has done. It helps you analyze your blood, right? It helps detect whether airborne pathogens exist, right? Is there Legionnaires, right? It tells you whether there's anthrax in your mail or not. Hopefully. Okay. MEMS have become ubiquitous in the world. And a car today, if you buy one new, if you're so lucky you can buy one new, has about 30 micro electromechanical devices in them. Everything from the thing that measures your air pressure in your tire to deploying your airbag to measuring how much fuel send. All right? All those things. Matt? Yeah?
Are they doing any integrating with forensic profiling and using computers, that type of...
Oh, what a great point. So there's things called sensor fusion, right? Which is to say, I have a sample of data, and maybe I know, I don't know, the pH. That's a bad thing. But, I know pieces of data about something, right? And the question is whether I can create a story, right? Do detective work, as you're saying. Okay? One thing that's happening today is to tell whether this phone has been in Germany last week, for example. Amazing it sounds. But there are ways to detect that. Bi-sensor fusion algorithms, right? And doing forensic work like you're saying. So yes, okay? The field, to me, was interesting because I was interested in electronics, semiconductor stuff, right? Transistors, chips, microprocessors, memory, all that stuff. But then something came out in the early 80s that was a pressure transducer. Somebody took a pressure transducer, which normally gets welded, a bunch of metal, and they made it on a chip, the same way they made transistors. And the cool thing about this is you can see the membrane deflect on a pressure transducer, right? Mechanics, something's moving under a microscope. You can't see electrons very easy, right? That's why you got to focus differently, right? Or whatever. Anyway, so let's look at a pressure transducer. What's a pressure transducer? All right. I'll create a simple one. And Matt makes these. So, no fair answering questions.
I'm not intending to.
All right. Pressure transducer has something mechanical that bends with a change in pressure. Okay? Membrane, right, can do that. Did you do the thing in elementary where you put a rubber sheet over a can and you tie a straw to it and you watch atmospheric pressure change the little rubber sheet, right? Goes up and down. Okay, rain comes and that kind of deal. Well, that's a pressure transducer, really. And today they're made the same way. Hmm? Yeah, man.
Is it like what they use in thermostats where they have like two different metals on a strip?
Different kind of thing.
Yeah.
I'll describe that. That does also create metal that bends, but it's due to temperature, all right, and different temperature responsive materials, not pressure, not direct pressure, right? What's pressure, right? In high school chemistry, right? Maybe this equation. Okay. Oh man, wow, yeah. I hated that question. Okay. Anyway, this is pressure, right? Right? And it's due to molecules bouncing around and hitting things, right? Whether they're air or argon or neon, whatever it is, some gas, right? Creates a pressure in some volume, right? With some fudge factors that chemical engineers love, right? That's the definition of a chemical engineer, by the way, is somebody with a handbook and just a bunch of fudge factors. It's harder than that. Temperature, okay? I pick on those guys. So this thing reacts to pressure differences. Typically, this is sealed off. So if I change the pressure here, right, I create a cavity, right, and this thing moves up and down depending on the difference in pressure, which times area creates a force, right? Difference in force. How could I detect that? How could I tell if that membrane deflected? What are ways you could sense deflection of a membrane? Right? How do you sense things? MEMS are sensors, right? MEMS include sensors, right? We call these things sensors, right? They may sense temperature, they may sense pressure, acceleration, all kinds of physical parameters. They may sense hydrogen, gas. They can do that, right? But basically, I've got some means, I need some means to sense that deformation. And here's what some clever people found out. A guy by the name of Obertufte in the early 60s, is that if I take some semiconductor material, like silicon, maybe it's esoteric. It could be some other semiconductor. But silicon is the stuff that makes up chips in your computers right today. And I changed the electrical properties of it. I can actually I find that as this material moves, as a strain is developed in it, and for you MEs, right, a strain is a change in length over length, right? The resistance, the electrical resistance of this changes. What is that? Sensing. So some people call this a transducer, right? Transducer. Important word. It changes a mechanical quantity, pressure creating a deflection, into an electrical property, change in resistance. How do you detect a change in resistance? Well, you put a current through it, you measure a voltage, right? Something like that. Okay? So, clever people in the 60s took metal films and they welded them to a little cylindrical package, and then they glued these resistors on there. Okay? And they made pressure sensors, used all over the place. One thing happened with these sensors is that, as electrical things will do, is they require power. Okay? All right. So I'm going to talk about an important set of words that occur in engineering a lot. Figure of merit. Right? How good is something? A lot of times you'll create some parameters that are really important, and then maybe some others that are not so important. Okay? And you can weight them, add them up, and average them and say, okay, well, this device is this much better than this one. Okay? Sometimes these can be fairly arbitrary, and they may violate all dimensions known to man, but they can be helpful in guiding comparisons, right? So, if we try to look at the figure of merit of this pressure transducer in the 60s with this metal thing, it turned out that the thickness of this membrane that they made was about 25 micron. What's a micron? Huh? What is a micron? How many microns in an inch? Start loading your toolbox. Dimensions are critical for engineers, right? Yeah. Yeah? 1/millionth of a meter, okay? 1/millionth of a meter. So 1 micrometer, 10 to the minus 6 meter, right? And it turns out, if you're an English person, it takes 25.4 microns, right, to equal 1,000th of an inch, or a mil for MEs, okay? Your hair is about 2,000ths of an inch, so that's about 50 microns, right? That's about it. So they were making membranes about 25 micron thick, okay? The power it took to operate this thing was about 5 milliwatts. And it could, what's important if I want to know pressure is, it's 15 psi in my tire. That's nice. Plus or minus what? 5 psi? Not too good, right? Could be 10 or 20. So there's something called resolution, or really better stated, accuracy, right? And other things like dynamic range. We won't talk about that. But basically, we'll talk about force resolution. And this thing could resolve things on the order of a millinewton. Oh boy, what's a newton? Right? Look it up. Okay. Not the guy, the unit, right? Okay. So you might look at this and say, oh, that's nice. Okay, I can resolve a force at a given power with that kind of a geometry. Another thing that's interesting, well, how big is this thing? What's the area? Right? This thing was about, 10 square millimeter, right? About a centimeter by a centimeter, roughly. Okay? Right. Well, half a center times half a center, somewhere in that neighborhood. Okay. ROM. Okay. Well, that's nice, but it's kind of big. It's kind of power hungry. That would drain even a AA battery fairly fast, right? Can we do better? And so what happened was, MEMS happened. Some clever engineers looked at that thing and said, boy, that almost looks like a wafer. That almost looks like a semiconductor device could make that. And so sure enough, people took this design and they made the first integrated pressure transducer. It became used as the MAP sensor, the manifold air pressure gauge in numerous GM vehicles at the time. Joe Giacchino at GM bought them, right? And they were great. Because why? The thickness went to 1 micron. That meant the area could go way down to under a square millimeter. The power went down maybe half a milliwatt. Order of magnitude, right? Just moves a decimal point. Pretty nice. And now we're down somewhere around a micronewton. 3 orders of magnitude. Okay? And here's the other funny thing. The price went way down too. All right? Oh. System engineers love that, okay? The cost went way down. So if I'm looking at a figure of merit and I average all this stuff, that looks like a tremendous improvement, right? And that's what the field of MEMS has been doing. It takes existing transducers, also actuators, which are the opposite of a transducer is, a transducer senses the environment. And to do that, it has to exchange energy with the environment, right? Oh man, what does that mean? So if I measure the environment, I had energy working on it, I changed the environment when I was trying to sense it and I screwed it up. Oh man, that's why this is so important, right? I don't want a lot of power. It screws up my measurement, right? Very important. So this was about the late 70s, 80s, churning away. Pressure transducers become ubiquitous in the world from a chip. They're made at plants like Intel, right? And today what's happening is something truly amazing. I'm just going to throw the numbers up. I won't explain much. But this is going to something on the order of 100 nanometer, 10 to the minus 12 watt, 10 to the minus 18 newtons. Still around 1 millimeter, but let's say a half millimeter square, okay, for about a quarter. Okay? And in fact, these can be interrogated not just electrically, but optically. How cool is that? You shine a light on it, it tells you what it is. It tells you the force. Hardly any energy of interaction, right? You can put it anywhere. You can power it with the sun, or maybe the vibration off a bridge, using something that can charge a battery, right? Okay? Portable electronics. Love that. Okay? So what I really want to show you, it's an example of how technology evolution, right, can breed devices that help us make our lives better, standard of living, right? These can be put in throwaway glucometers, right? All kinds of crazy things, right? And it's the field that is growing very rapidly today, right? The MEMS market today, and this includes things like temperature sensors, accelerometers, gyros, all this good stuff, is about somewhere, depends on who you believe, called $11 billion a year. Okay? One segment of the market went from $10 million 6 years ago to $3.5 billion. All because of the iPhone. All right? But you know the iPhone. Amazing. What's that? If you do the numbers, it's something like 200% a year growth. Okay? So, does the market want it? I think so. Right? That's where marketing did their job. Maybe they predicted this. They probably didn't. But someone listened to the customer. Someone was saying, yeah, that iPhone's going to displace all those StarTACs. Right? If you had one of those. Which it has. Right? It's amazing. Okay? This is what MEMS is doing today. Okay? So a little bit about what I do and what the company Matt talked, HT Micro does, right? We got 5 minutes, 10 minutes?
We got 12 minutes.
12 minutes. Has to do with this area of MEMS, okay? And we're just starting to pick on more electromechanical devices. Okay, we mentioned gyros, accelerometers. Those are sure nice. Pressure transducers. Boy, everyone use an inkjet printer? You know, things you spend a fortune for ink on, right? It's a real pain in the thing. It never works either, right? All those nozzles are made with the same process used to make that pressure transducer talked about, this one. All right? Okay? Precision engineered things, right? And the issue there is, an important idea is, when you miniaturize something, right, can you maintain the same precision, really the same accuracy, the same tolerance as you can as a large scale? All right? Let me offer this to you. Everyone knows a machine shop? Been to a machine shop? See all these lathes and mills and metal filings coming off, right? Right? You've probably seen brakes if you worked in construction, right? Bend metal and stuff like that, sheet metal. Okay? I go to a machine shop and I say, I'm making a shaft for a car. Okay, it's my, it's coming off the wheel, right? And they say, okay, what is it? Well, it's nominally 1 inch in diameter, okay? They say, it's 1 inch in diameter. Okay, that's nice. How many digits in that 1 inch? Significant digits you talk about, right? How many? 5, did I hear? Who said 5? Okay. Let's put in 4. Okay. It's got 4. Yikes. And the machinist says, yeah, okay, I can maybe hold that. It's going to cost you some. It's going to cost you some, but they can do it. It's kind of on the edge of doing things. And they make it, and it's beautiful, and you measure it and say, yeah, he did a good job. Okay. And then you come back next week and say, you know what? My design requirements have changed. This is now not 1 inch, it's 1 millimeter. Oh, and you did what for me? You gave me 1 part in 10 to the 4th. 1 part in 10 to the 4th. 1 part in 10,000. I want 1 part in 10,000, please, at a millimeter. What do you think they do to you? Yeah. Right? Or they lose their lunch or something. Not good. They say, can't do it. Intel can't even do it. Okay? Intel has trouble doing it. Okay? And that's what is this notion of maintaining tolerances at small dimensions. And it underlies the technology in this field. Okay? Tremendous problem for metrology. We talk about metrology measurements, right? How do you measure that thing? That's hard, let alone making it, right? So a lot of new technology has to be developed to support this industry, right? I dare say that's becoming almost as big as the MEMS market. In any event, right, when you take a look at a pressure transducer, you ask yourself, gee, did I maintain tolerance? 25 plus or minus what, 1 micron? 1 micron plus or minus 1/25 of micron, right? And you'll find when you do the mechanical engineering, some of these things just don't scale easily. They have very nonlinear effects. They go crazy if they're off by a little bit, right? There may be cubic dependencies on these, right? In any event, it's a field that uses about every engineering discipline that I'm aware of. And so, if you're interested, I encourage you to ask Matt further because he is an expert on MEMS, right? So, what do we do at HT Micro? We took one device that's existed for 80 years. In fact, it's not too far off from the incandescent light bulb. It kind of looks like it. And some of you may recognize it. I'll pass it around. Maybe I'll pass it around this way. It's easier, right? That's called a reed switch. It's a magnetic reed switch. What it looks like is a tube of glass, like a cylinder. Okay, you'll see it's kind of greenish color glass. It's got 2 leads sticking out. Yeah, those are wires. Okay, and inside the tube are 2 bars of metal. We call them cantilevers because they're actually anchored here and here. Okay, and there's a little seal. Okay, and we call this hermetically sealed because it's impervious to any gas. That's a lie, but it's pretty good. If it gets immersed in water, it's not going to go in there, right? And these bars are interesting because they're also magnetic. They're conductive, they're wires, but they also respond to magnetic field. So if I take a magnet, right, like the thing in your earbud, right, which is pretty strong. If you've ever put 2 earbuds together, you know they fly apart. If I take a magnet and put it near this thing, it turns out these 2 ferromagnetic blades attract to each other. That one goes that way, that one goes that way. And they short themselves out. Huh. A magnetic switch. Right? This was first patented in 1920. Okay? And it hasn't changed much since then. That device you see, you read right off the patent. Okay? What good is it? What can I do with that? Does anybody have ever seen an anemometer? Measures wind speed. So those things go, right, up on a weather station or something, twirls around. In every anemometer, you'll find one of these. And there's a spinning magnet in that rotor. And this thing opens and closes every time that thing turns around. It's a good way to measure wind speed, right? You may have an alarm at your home. You open the window, it's got a little detector, window's open, right? Call the cops, whatever. Something, hopefully. Anyway. Nice position sensor, right? Is my oil level too low? Put a magnet in the oil, let it float past the sensor, it tells it's too low. Stop, don't burn up your engine, right? What have you. Reed switches are used all over the place. There's about 1 billion of them made every year. Right? Using everything from medical devices to automobiles, right? So what we did at HT Micro is we said, that thing is way too big, way too fragile, right? If you drop it, it's glass, it can break, right? And not too amenable to modern PC board techniques. So what we developed is we took that thing and integrated it on a wafer. We made a process whereby we can create these blades, create the hermetic cavity, create these leads, and put it all on a little chip and make tons of them at a time. Because I'm putting it on a wafer. That's the great thing about chips, right? Intel loves it, Motorola loves it, or Freescale, whatever they are. Soon to be Google, I guess, or something. Anyway, they love it because I can make millions of them at the same time. And that's how I drive the cost down. Economy of scale, okay, manufacturing. So this is what we do. The device you see in that little paper, there's a few hundred of them, right, are equivalent to this glass enveloped component, okay? Well, what good is that? Two things you want. I would like to make that smaller. That's nice. I would like to make it more reliable, right? 2 words, hopefully cheaper. 3 words that all engineers will be interested in. Smaller, more reliable, cheaper. Yikes. But remember, this sort of our A1 design criteria. So one application we're serving today is in something called a pill camera, right? Where you swallow basically a pill and it images your intestinal tract, right? It obviates a colonoscopy to some degree, right? If you're fortunate enough to get that done. In any event, that's a case where a device needed to be made that was small enough to fit inside a pill and not affect all the other electronics, the CCDs, right, the power source, right, the A to D converters, the tremendous amount of data processing, etc. And then this thing gets wired out to a belt you wear, okay, all right. All kinds of medical devices have them of interest. So, if we have time to do this, you can see how they operate. This is a card used as a demo. And down here is a magnet. Okay, and you can slide the magnet across the switches, and you can see them turning on their corresponding lights, right? We call this an integrated reed switch, right? Truly integrated device. It's a MEMS device. It's micro, electro, right? And mechanical. The thing moves, right? It's not like a transistor switch. It's a truly mechanical switch. And unlike a transistor switch, it doesn't require any power, electrical power, to sense the magnetic field. We call it a passive electrical switch. Another important aspect of sensors today. Here's one other switch, and I'll stop. This switch doesn't operate with a magnetic field. It operates by sensing acceleration. Okay? It's an impact switch, right? And you can operate this thing by resetting this little press thing and just drop it or kick it or whatever you want to do. All right. Also used in cases where I want to passively interrogate motion, right? Oh, did I pick this up? It'd be nice to know that without something that's draining power from my battery, right? Hearing aid companies love it because, oh, there's a cell phone next to my ear, right? I can sense a magnetic field with a reed switch. It doesn't drain battery from a power from a battery. Okay? So that's a taste of MEMS. Again, it's a field Matt knows well. I hope you'll, if you're interested, interrogate him more about it. And I wish you all well. It's hard work, but it's worth it, right? If you have a passion for it, you'll fall in love with the field. So I encourage all of you to pursue it. Anything I can answer for you? Any questions about MEMS engineering? Come up. All right.
How'd you get into it?
I saw a paper in 1978 by Kurt Peterson. It was in the days when you had to go to a library and make mimeographs. Okay? You actually had to write out a card and tell the librarian, I want that journal, and they went and got it and put it on there for you, and you copied it in a copier or whatever. And this gentleman is a true mentor of mine, and I hope you will all find mentors in your respective careers. But he, for the first time, really identified a lot of ways in which one could take electromechanical devices and integrate them on a chip. Right? He's now successfully started 5 companies, including one which does sense anthrax at your local post office, right? Called Cepheid. He's an astronaut too. That's why he names all his companies after astrophysical things. But he created Nova Sensor, first MEMS pressure sensor company, right? He basically turned me on to MEMS when it wasn't called MEMS. It was something. He wrote a paper called Silicon as a Mechanical Material, when most people thought semiconductors were just good for electronics. He realized that silicon is a very strong material, in tension at least, turns out. And so proceeded to create a number of accelerometers, keyboard sensors, right? All kinds of things. Optical displays. That thing you see in there had a precedent at IBM in the late 70s. TI really did it, but they were thinking about it, for sure. Okay? The DMD, the multimirror display. Another MEMS device, right? Okay? So, for me, it was the linking of the 2 disciplines, mechanical with electrical. Sounds like a challenge. And the field has really blossomed. So, again, something Matt knows a lot about. If you guys are interested, you're in the perfect place to learn more. The perfect place.
Can you say a little bit about your company, when it started?
HT Micro, yeah, I'll give you 30 seconds. It's a startup which was created with seed money, some call angel money, to make use of a technology called high aspect ratio microfabrication, which is taking a component and extruding it out of the plane of a chip. So transistors are flat things, right? If you open up your memory, right, and you take the thing off, you just see a bunch of flat stuff, pretty colors, right? But it's all flat. There's nothing sticking out. Because it's hard to maintain tolerances when you start trying to get things to stick out of a wafer. And that turned out to be something that we specialize in. And that's convenient when you want to interact with magnetic fields or inertia, acceleration, right? You need mass. When you need more 3-dimensional things. So HT Micro specializes in particular in fabricating electromechanical components out of the plane of a wafer. It's really the unique part of HT. Been in business for 10 years, right? We're hiring, expanding, built a manufacturing plant last year in Albuquerque, right? One of its only kind in the world. And definitely looking to hire good engineers. And all kinds of people. Even accountants. Attitude's important. Take accounting. Take finance. Take technical writing.
No HR yet, though.
That's right.
To avoid that.
We outsource that.
What's that?
You can outsource that. So again, I'm happy to take any of your questions. I realize we're over time, so I know you guys are busy and have to go, but thanks for your time and having me, and good luck with the course and your careers. Very well.